This is Catherine Nightingale of Chattanooga State Community College, and this video is for linear algebra on the topic of a basis of a subspace. A basis for a subspace H of Rn is any linearly independent set in H that has to span all of H. You can think of this as the minimum set of vectors that span the subspace. The reason why we would look for a basis is to see certain properties of the subspace and also to compare subspaces. Because sometimes you have a spanning set and it doesn't look the same as another spanning set, but when you find the basis of each, you find that it's the same basis, and so the sets are actually the same when you take their span. So you can use the basis to compare subspaces. Okay, so over on the left we have basis of a subspace, and I'm reminding you of the definition we just talked about: any linearly independent set in H that spans H. Now just a couple reminders. This first one is from section 1.7. and it says that the columns of matrix A are linearly independent if the system AX equals 0 has only the trivial solution, meaning no free variables. So that's how we will test to see if our vectors are linearly independent or not. This second statement is from section 1.4, theorem 4, and it says that the columns of an m by n matrix A span Rm if and only if A has a pivot in every row. So we are going to be checking our matrices for linear independence to see if it has a pivot in every column, meaning no free variables, and we'll be checking it to see if it spans the space by looking for a pivot in every row using that theorem 4. So let's look at a couple examples. First one, do the following vectors form a basis for R3? Well, we know they're sitting in R3 because they have 3 entries each. Now, what I'm going to do is put them into a matrix, 2 0 0 1 1 0 5 1 3. So I put them into the matrix as the columns, and then I'm going to row reduce. So here's my row reduced matrix. So now I'm going to use those properties from the last slide. I see that there's a pivot in every row. So from theorem 4, the columns span R3. Now I look for linear independence. There's a pivot in every column. So AX equals 0 has no free variables, and so the columns are linearly independent. Now these vectors now meet both criteria for being a basis of R3. It spans R3 and they're linearly independent. So we conclude that they're a basis for R3. Okay, here's a different set of 3 vectors. We're going to perform the same check on these. So I'm going to start by putting them into a matrix. I'm going to call them U, V, and W. And actually, if we look at this, we can see visually that U plus V equals W. And so automatically we know that these vectors are linearly dependent, meaning that they cannot be a basis for R3 because it fails that criteria. Now, you won't always be able to see it so clearly right off the bat, especially if you had several vectors with maybe 5 entries and 5 vectors. You might not see the dependence relation so easily. So let's go through the process you could follow for any set of vectors. Put them into a matrix and row reduce. That's your first step. And now you look at the pivots. So I see that there's no pivot in column 3. which tells me that ax equals 0 has a free variable, which tells me that u, v, and w are linearly dependent. So I have the same result as what I saw over on the left. So my conclusion is they're not a basis for R3 because they're not independent. Now alternatively, in this matrix, I could have looked at row 3 and seen that there's no pivot in row 3, meaning that the columns do not span R3, and I would have gotten the same result, that these vectors are not a basis for R3. Okay, now we're going to shift gears a little bit, and we're not looking for a basis for R3 anymore. We are looking at the subspace defined by the span of these 4 vectors. And we want a basis for that particular subspace. So we're no longer looking for something that spans all of R3. We're just looking for some vectors that span this subspace. So the key will be to find the linearly independent vectors that span this subspace, and those are going to be the pivot columns of the matrix if I put these vectors into a matrix. So that's what I'm going to start with. I'll call them v1, v2, v3, and v4. And I put them into a matrix, I row reduce, and then I look at my pivot columns. So I see column 1 and column 3 are pivot columns. Okay, now let's look at this -2 in column 2. If I compare column 2 to column 1, I can see that I can rewrite column 2 as -2 times column 1. So v2 is -2 v1. You can see that by looking at your original matrices, or original vectors, 3, 2, 3, and -6, -4, -6. v2 equals -2 v1. Now if I look at the 4th column, I get the relationship v4 can be rewritten as -6 times v1 plus 2 times v3. I'm just using the columns of this reduced matrix to get this relationship. So what happens is we can see that v2 and v4 depend on v1 and v3. So this tells us that v1 and v3 will span the entire subspace. We don't need v2 and v4 to get to all the elements in the span of these 4 vectors. Okay, next I'm going to look at those pivot columns. v1 and v3 are linearly independent because they have a pivot. And so v1 and v3 are going to form my basis. So my basis is 3, 2, 3 and 9, 7, 6. So this is the process if you're asked to find the basis of a subspace of R3. Put your vectors into a matrix, row reduce, and the pivot columns will form your basis. So the pivot columns of your original set of vectors. This will be your process for finding the basis.